This is part 5 in a series of videos about stardust. In this episode, we're going to talk about the space around stars where dust forms, and in particular, the pressure and temperature in those environments. So in our previous video, we talked about condensation sequence and how different things will form at different temperatures. We introduced the idea that you could plot this space where we have temperature on the y-axis and pressure on the x-axis. It is decreasing to the left. It is a log scale, temperature increasing up the axis. What we see here is if we concentrate on this pink line, this is Al2O3, so that is aluminium oxide. And we have what temperature it can exist at as a solid depends on the density in the gas. So if the gas is too low density, then you won't have a stable solid and it will sublimate back into a gas. And so what we can see here is that at very high pressures, we're going to form Al2O3 above about 1550 Kelvin. But as we go down in pressure, we can see as we go through a few orders of magnitude in pressure, down here, we're now down below 1400 Kelvin for the stability temperature. What we're also showing on here is these lines that are in the dot dash style, those are the calculated trajectory of the pressure and temperature in the region around the star based on the mass loss rate and the expansion velocity. So we have material flowing off a star at a certain rate, and so you're going to have a certain density of gas that's going down as it spreads out into a bigger and bigger volume. And so you can see that represented here. It's moving away from the star, so it's going down in temperature, but it's also spreading out, so it's going down in pressure. And so we can see here that for this one, that's a fairly high either mass loss rate or low expansion velocity, it's going to form the Al2O3 around 1525-ish, 1530 Kelvin. But if we go to something with a much lower mass loss rate, so this pink line over here, what we're seeing is that now we're well below 1400 Kelvin. And so we can easily see how, depending on how much material the star is losing and how fast that material is flowing away, it's going to affect what temperature things form at. This is calculated using this equation, which I'll come back to, which is basically relating the mass loss rate and the expansion velocity of the material coming off the star and the distance from the star to the density. And we use that with the ideal gas law to derive a relationship between the pressure and the temperature, and it's based on the mass loss rate, the expansion velocity, and the luminosity of the star. So let's start by talking about, well, what distance from a star does dust actually form? So here I have my AGB star, and material is flowing away from the star as it's being levitated and pushed away. And at some distance, it's going to be cool enough to start forming dust. And so it's going to form out here. So this radius at which it's forming, that's basically the inner dust radius, and it is the inner radius of the dust shell. It's where the dust is first stable. At this distance, the dust temperature has to be an equilibrium between the energy absorbed from the star, so it's absorbing light from the star that heats it up, and it's emitting energy according to its temperature. For a dust grain, it's only going to intercept a tiny little fraction of the star. That's going to be depending on its surface area, in fact, its cross-sectional area. The dust grain is only lit up on one side. So effectively what you have is a cross-section capture area that is just the pi r squared for a sphere. So in this case, we have RD, capital R, uppercase RD, is the radius of our dust grain. And then at this distance from the star where the dust grain is, that is going to receive a flux, FD. So remember that we've got starlight that is flowing out, and at some distance from the star, there will be a flux through a surface area at that distance, and that is the light that the dust grain is intercepting. Now, for a star, it has its luminosity flowing out in all directions. Once you get to a distance RD from the center of the star, that distance is now the sphere over which the energy is spread. And so now you've got to spread that luminosity out over a much bigger surface area. And what we have as flux is the energy per second per unit surface area. And so what we've got is the luminosity of the star, and now it's spread out over a sphere of radius RD. And so this is the distance from the center of the star to where the dust is. luminosity is related to the flux and the size of the star. So we've got the flux at the surface of the star and the radius of the star. And so this is what the luminosity is. And we can simplify that, getting rid of the 4 pi's. And we end up with this equation for the flux at the distance of our dust grain is related to the distance of the dust grain, the radius of the star, and the flux at the surface of the star. Dust grains are not black bodies. That means they don't absorb everything that hits them. In fact, they have some reflectivity. So we call this reflectivity albedo. It is the fraction of incident light that is reflected. And what that means is that if a fraction of A is reflected, then a fraction 1 minus A is what is absorbed. So we have to put that into our calculation. So we've got a flux through a certain area, FD, that's at the distance of little rd. We've got the cross-sectional area of our dust grain, pi big RD squared, and then we've got the fraction that's actually absorbed, 1 minus A. Now, we already worked this out and on a previous slide that the flux at the distance RD is related to the flux at the star and the radius of the star. And then we've got the energy absorbed has to equal the energy emitted. So what is the energy emitted by our dust grain? Well, it basically is the luminosity of the dust grain, which is given by its temperature. So it's going to give off a flux through its surface area that is given by sigma T d to the 4, where this is the temperature of the dust grain. And this is the surface area of the dust grain. So this is how much energy is going in, and this is how much energy it's putting out. So now we can equate those two. So this is energy out, this is energy in. And this is that other equation for FD, because I want it in terms of the qualities of the star. So I've put these together, and I've also included that the flux from the star is sigma T star to the 4. Remember, this is the Stefan Boltzmann law, F equals sigma T to the 4. So now I've got those two put together, and now I can do a bit of canceling things that are on both sides. So I've got a pi RD squared on both sides. I've also got a sigma on both sides. And so that simplifies down to this equation. So I've got TD to the 4 equals 1 minus A over 4 times R star over RD all squared times T star to the 4. And obviously we're going to want to take the 4th root of that. So now we end up with this relationship. So we've got the temperature of a dust grain is given by 1 minus the albedo to the 1/4, the 4th root, times the square root of the radius of the star over 2 times the distance of the dust grain, times the temperature of the star. We use this for planets, we use this for asteroids, we use this for dust grains. So now let's consider that we've got a relationship now between the radius and the temperature, right? So we've got our inner radius is actually going to be set by what temperature it can exist at. So just taking that same equation we had before, but now we're calling it T inner. So we're specifically attributing it to this innermost dust, the dust where it first forms. For right now, we're going to assume that we're using something like graphite or amorphous carbon, or even some of the silicates that are dark in color, that their albedo is so low that they basically absorb everything. So we're going to assume albedo is nothing. And so we've got a nice simple equation with the temperature here being related to the star temperature and dropping down as the square root of the distance. That's that equation with the relationship between the inner dust temperature and the star temperature. So now all I've done is to rearrange this equation. So the Rn now is this R here. This is the distance at which the dust is forming. And so I've rearranged it to get this out. And so I've ended up with this equation here. So the inner radius is given by the radius of the star over 2 times the temperature of the star over the inner dust temperature all squared. Now, since stars are more or less black bodies, we're going to assume that they behave like black bodies for the purpose of this. And so we can actually put this in terms of luminosity. This is good because radius isn't something we can directly measure, but luminosity is something that we can measure for a star. So we're going to put in the luminosity as 4 pi r squared sigma T to the 4 for our star. We've extracted this R from this equation. So we now have an equation for R in terms of the luminosity and the temperature, and we're going to plug that into our inner radius equation. And now we've got our inner radius equation with luminosity in it. And now we're going to do some simplifying. And we end up with an equation where the inner radius is given by the luminosity and the inner dust temperature. And it goes as 1 over the inner dust temperature squared, and it goes as the square root of the luminosity. Now that we've got that, we need to start to incorporate the pressure piece of the pressure temperature space, because we don't know what the inner temperature is until we know what the pressure is. And for that, we need the ideal gas law. Most physicists originally learned the ideal gas law as PV equals nRT, where P is pressure, V is volume, T is temperature, N is the number of moles of gas, and R is the universal gas constant. Now, moles are not a very useful thing in space, so we're going to do some converting here. So the number of particles in a mole is Avogadro's number, N sub A. And so the total number of particles that we have would be N, the number of moles of gas, times the number of particles in a mole. So N tot is N times Na. So N is N tot over Na. And so I've just substituted that into my equations. Now I have PV equals N tot over Na times RT. And now we're going to take the universal gas constant and Avogadro's number, and 1 over the other gives us Boltzmann's constant, K. And so that simplifies this further. So now we have PV equals N tot KT. Now we're going to take the volume and divide that out. So now we've got P equals N tot over V times KT. But N tot over V is just the number density of particles. It's the total number of particles divided by the total volume. So we have a number density of particles, little n or lowercase n. And so now we have that the pressure equals NKT. That's the number density of particles, the Boltzmann constant, and the temperature. And we can actually take this one step further and convert the number density of particles to the mass density of particles, where we're putting in the mass of the particles and the mass density. Now, the next thing we need to think about is the material flowing off the star. So I'm going to start with just a basic fluid dynamic thing, where if we have a mass flow rate of a fluid, and that fluid has a density rho, and it's flowing through a tube or pipe of cross-section area A, and it's flowing at a velocity v, then we get a mass flow rate of m dot, dm by dt, equal to rho AV. Okay, so that's the density times the area times the velocity. Now, if we apply this to the mass flowing off our star, we have a mass loss rate that is given by the density and the area into which it's flowing and how fast it's flowing. And in that case, what we have is a mass loss rate, m dot, and an expansion velocity of our material flowing out into space. We have a density at a certain distance from the star r, and we have a radius over which it's spread. So we have a surface area. It's flowing through the surface area 4 pi r squared. And so now we're just taking this equation, we're rearranging this mass flow rate equation to be rho equals m dot over AV, and we're putting in the area of the sphere into which the gas that's flowing off the star is flowing. So we have this now that gives us measurable quantities for the star, the mass loss rate and the expansion velocity, to give us the density at distances from the star. Here again is that rho is a function of distance from the star, and here we have pressure and temperature related through density. And so we can put those together and we get an equation that looks like this. So we've got pressure at point R is related to temperature at point R by this equation, where we have the mass loss rate and the expansion velocity and the distance r and the mass of the particles. So now we're going to get rid of some r's, because r's aren't actually very useful to us. We just want a PT space. So remember, we did this before. We worked out that the relationship between the distance r and the temperature of the dust depends on the luminosity and the temperature. And again, this is not including any albedo. So now we can put these together. So basically, I'm going to substitute in for my r, my distance from the center of the star, with this quantity here. And when I multiply everything out, I end up with an equation that looks like this. So I've got the pressure in terms of temperature, and all the other things are either constants or measurable. If we look at this, here's pressure, goes as temperature to the 5. Here's mass loss rate and expansion velocity. Those are things we can measure from carbon monoxide observations. In particular, because in the radio we have nice narrow lines that we can see from carbon monoxide molecules, we can use the Doppler effect to get the expansion velocity. And we can also use the strength of the lines to get how much material there is, so we can get a mass loss rate. So we can plug those in. Luminosity of the star is measurable too. And then we have sigma and K are the Stefan Boltzmann and Boltzmann constant, respectively. And then M is the mass of the particles. In this case, it's going to be mostly hydrogen or possibly molecular hydrogen, so a mass of 1 or 2 AMU. And so let's look at what this does when we actually put these together. So here I've got a pressure temperature space. I've got pressure on the x-axis, temperature on the y-axis. It's a log scale on the x-axis. It's linear on the y-axis. What's plotted on here are actually the calculated stability temperatures for some dust grains. So here I have carbon, and you can see here it depends on the carbon to oxygen ratio. We'll come back to this later, but it can be easily understood in terms of, as long as the carbon to oxygen ratio is above 1, all the oxygen is consumed in carbon monoxide, and so the excess carbon is available to make dust. But when you only have a very small amount of excess of carbon, the partial pressure of carbon is low, and so the stability temperature is low. As you increase the amount of carbon that is left after making carbon monoxide, you will increase the temperature at which the carbon can form. You can also see here, silicon carbide is forming at a slightly lower temperature than just carbon, but this stuff is not sensitive to the carbon to oxygen ratio, and that's in part because it's dictated by the abundance of silicon. So this is what temperatures things should form at. Now, this is basically the same thing. I've got my carbon to oxygen ratio lines for different carbon condensation temperatures. And all of these are the calculated pressure temperature paths for the material flowing away from the star. And as it flows away, you're using the mass loss rate and the expansion velocity to work out what the pressure temperature space is. And so what I've got here is my pressure temperature space. It's moving away like this. Depending on what my mass loss rate and my expansion velocity are, I will follow a different trajectory. What you can see here is that it really matters what my carbon to oxygen ratio is. So if I take this line, for instance, if it got a carbon to oxygen ratio of 2, we're going to have dust forming right around 1800 Kelvin. But if it's down around 1.05, now it's down below about 1500 Kelvin. So that's a very important point. Let's take another look at this. And in this case, what we're looking at is just stars for whom the carbon to oxygen ratio is approximately 1.05. And what you can see here is that actually it's not very sensitive to the pressure. So for all of these stars, the carbon to oxygen ratio is what dictates what the formation temperature is going to be. And it's going to be around 1500-ish, just under 1500 Kelvin for all of these stars. If we were to increase the carbon to oxygen ratio, it will be a higher formation temperature. And so this is something that we can now use to understand the environments around our stars and work out what's the inner radius and use it in model inputs and so on to understand exactly what's going on in dust formation around stars.